So, good morning, everyone. My name is Mattia Piccinini, and I'm a postdoctoral researcher at the Technical University of Munich. And the title of this presentation is Kineto Dynamical Planning and Accurate Execution of Minimum Time Maneuvers on 3D Circuits. And as a motivation example, let's look at our TUM autonomous Indy car, which is spinning around in this video in a highly banked oval racetrack. And this was because the planned velocity was invisible in this scenario, which highlights the challenges of driving autonomously at high speeds on three-dimensional racetracks. And indeed, the existing autonomous racing agents cannot drive at the limits on 3D tracks. And so to address this, we propose a new artificial race driver, which replans new trajectories every 100 milliseconds using minimum time nonlinear MPC, and then executes the planned maneuvers with model structured neural networks, and finally closes the loop on a vehicle. And this presentation focuses on the trajectory planning part, so the green box. And for trajectory planning, we solve online nonlinear MPC problems, and we want to minimize the maneuver time T, subject to a new Kineto Dynamical model on 3D tracks with learnable yaw rate and lateral velocity prediction models. And we have learnable maximum performance acceleration constraints with the new formulation. And finally, some boundary conditions. And we devise a multi-round learning scheme to learn the vehicle dynamics and the maximum performance. So the first round uses open loop standardized maneuvers to start learning the vehicle dynamics. And then we proceed with 4 rounds of closed loop driving on a racetrack. And in each round, we retrain the planner and the controllers. And the fifth round finally learns the effects of a three-dimensional racetrack on the vehicle dynamics and performance. And in this way, the lap times actually decrease over the 5 learning rounds until reaching the final best lap time. And we deploy our agent on a high-fidelity race car model, and we compare our agent against a literature benchmark in red and against what we call MLT-VS in blue, which is the minimum lap time optimal control solution, which we solve offline with the full multi-body vehicle model to be driven. And so the blue car is actually the best lap time estimate we can obtain. But the blue car, which is ahead, represents an ideal lap time without execution errors and requires several minutes to be computed. And the lap times of our agents are better than the benchmark and are only 0.7 seconds slower than the MLT-VS. And this is the first time that an artificial agent can replan online and execute minimum time maneuvers and getting so close to a minimum lap time optimal control solution obtained with the same vehicle model to be driven. And our agent drives actually 3.5 seconds faster on the 3D track with respect to an artificial two-dimensional version of the same track. As our agent actually learned how the three-dimensional nature of the racetrack affects the vehicle dynamics and the maximum performance. And indeed, our agent can keep locally higher velocities and lateral acceleration, higher lateral accelerations on the 3D track in red in the top 2 plots, and is faster in many corner apexes by exploiting the banking angles. And finally, our agent generalizes zero shot to unseen tracks. Indeed, the lap times of our agent are very close to the offline MLT-VS, even on new tracks never seen during training. And this is because the physics-informed architecture of our agent learns the underlying vehicle dynamics and rather than specific maneuvers, right? So it learns really the vehicle dynamics and can generalize to unseen scenarios. So with this, we thank you for your attention. This is a link to our paper and to our autonomous vehicle systems lab website at the Technical University of Munich.